In this video, we're going to learn about Gauss's law for an infinite line charge, and we're going to use Gauss's law to find the electric field due to an infinite line charge of linear charge density lambda. So that's the charge per length of this line. So first of all, why do we care about infinite line charges? Well, it turns out that a lot of things in nature and in the world around us can be treated like infinite line charges. So DNA actually turns out to be very nearly an infinite line charge. Anytime we've got long wires and we've got electric current moving through them, we've got an infinite line charge. Anytime we've got a beam of charged particles moving in one direction or just sitting still, we've got an infinite line charge, or what's very nearly an infinite line charge. So there's lots of places that we end up seeing this infinite line charge in the real world. So before we do anything, we're going to try to use symmetry to simplify our lives. And so what kind of symmetry do we have for an infinite line charge? Well, if we just sort of look at it, we can kind of see that there's probably some sort of radial symmetry around the line charge. But if we zoom in on a particular segment of the line charge, so let's call this the origin, then any little piece of the line charge, so a little piece here, will make an electric field some distance away that points in this direction. And then on the other side of the line charge, there's an equal piece which produces an electric field that points in partly the opposite direction. And so those two will cancel or add and produce a electric field that points straight up or away from the line charge. And this we can sort of extend out to infinity. So we've got another piece here and another piece here, another piece here, another piece here. And if we keep doing that, we'll see that the x component, if we call this the x direction, will always cancel, and the component that's pointing away from the line charge will point straight away. And so this isn't just true in one dimension, this is true, everywhere around the line charge. So the electric field is always pointing outwards away from the line charge. And so this is called cylindrical symmetry. So we're going to want to use a cylinder as our Gaussian surface, because this gives us the greatest amount of symmetry. And the cylinder is going to be centered about our line charge. So all right, let's construct that cylinder. So let's say this is our infinite line charge, and it's got, say, a bunch of positive charge with charge density lambda. What is our Gaussian surface going to look like? Well, we said it was going to be a cylinder, and it's going to be a cylinder that's centered around the line charge. So it's going to look something like this. This is going to be our Gaussian surface. Let me just make it all dashed so that we understand it's sort of fake. We're kind of imagining that it's there. So this is our Gaussian surface. But how long should the Gaussian surface be? So what should this length L be? Well, it's not really obvious to me because, this is an infinite line charge. It stretches to infinity and back. So I hope that it doesn't matter what length this Gaussian surface is. So I'm just going to leave it as L. And similarly, what do we want the radius of this cylinder to be? Well, it would be nice if we could apply Gauss's law for any possible radius. So we could just plug something into this radius at the end, and then we have an expression for the electric field in terms of the radius. So I'm just going to leave the cylinder's radius as R. I'll call it big R for now. So great, now we have our Gaussian surface. There it is. It's a cylinder just centered about the line charge. And so now we can actually start using Gauss's law. So if we write out Gauss's law just states that the electric flux is equal to the charge enclosed by the surface divided by epsilon naught. And so let's start with the right-hand side. Let's try and figure out what the charge enclosed by this surface is. Well, the surface encapsulates an amount of this line charge that's just the length of the cylinder. So it intersects the line charge at these two planes here. So, or I guess it's close to like this plane and this plane, which cover a distance L. So the charge enclosed is just going to be the charge per unit length. So Q over L, if you like, times the length. And so this has the right units. This is our charge enclosed by our cylindrical surface. Now, what about the electric flux? So what about phi E? Well, we know that this is equal to the integral over our Gaussian surface of the electric field dotted with the area unit vector. Sometimes you'll see this written as ds instead of dA. So what is this integral? Well, let's start with the sides of the Gaussian surface, so the ends of it, the top and the bottom, if you will, or the right and the left. So these surfaces here. So which direction does dA point? Well, we know that dA always points outward from the surface, so it's going to point to the right on this side and to the left on this side. So this is our dA on the left, this is our dA on the right, and ignore the lengths, they're meant to be unit vectors. And which way does the electric field point? Well, we said that the electric field always points away from the line charge. In other words, dA and the electric field are at right angles to each other, so this dot product is equal to 0, because another way of thinking about it is that the dot product involves a cosine of this angle, and cosine of 90 degrees is 0. So this is phi E for the sides. I'll call them the sides of the cylinder, or the electric flux. What is the electric flux for the main body of the cylinder? So this region here. Well, it's not 0. We're pretty sure of that. Otherwise, this would be not a very interesting problem. So in this case, the electric field, we said, always points away from the line charge. So the electric field always points away. And similarly, the area vector on the surface of the cylinder also always points away from the line charge, because the cylinder is centered around the line charge. So because they're pointing in the same direction, the dot product just becomes the magnitude of E times dA. Now, the really nice thing about this is that because it's a cylinder and there's symmetry, the electric field is the same everywhere on the surface of the cylinder because of symmetry. So it's the same on the surface on the top and the bottom. It's the same on the surface everywhere on the surface of the cylinder. The electric field is the same. So this is just a constant here. And so we can pull it out of the integral, and we're left integrating just dA. But this integral, all this means is we're adding up all the little pieces of area of the cylinder on the main sort of body of the cylinder. So this is just equal to the area. So E times the area of the cylinder. And the area of a cylinder is just 2 pi times the radius of the cylinder times its length. And so this is the electric flux for the main body of the cylinder. And if we add this to 0, it's still the same thing. So this is our total electric flux. And so now we can finally equate both sides of Gauss's law. So we can equate the electric flux and the charge enclosed over epsilon naught. And when we do that, we get E times 2 pi r L is equal to Q enclosed, which we said was lambda times L, divided by epsilon naught. And so blessedly, we see that the lengths cancel out. And so that's great, because I was a little worried about that. We didn't really know how this length should have any meaning for an infinite line charge. So if we divide both sides by 2 pi r, then we get that the electric field is just equal to lambda over 2 pi r epsilon naught. And so this is our final answer in terms of the electric field, or if we want to write it as the electric field as a function of the radius of the cylinder is equal to this. And so we now know what the electric field is at some distance r away from the cylinder, and we didn't have to do any integration really. We just sort of said, oh, we're just adding up all the little pieces. So Gauss's law is really great because it lets us avoid doing really complex integrals. Finally, I'd like to thank all my patrons on Patreon. Your support is greatly appreciated, and it is you who makes these videos possible. If you aren't currently a patron, to get early video access, behind-the-scenes footage, exclusive content, and join a like-minded community, click the link on screen or in the description below. Thanks for watching.